Assalamualaikum warahmatullahi wabarakatuh and good day, our dear listeners. Welcome back to another series of lecture about mathematics in the modern world. Once again, this is Miss Norlailah and Madid, your video lecturer for today. For this video, we will be continuing our discussion on Chapter 3, Logic. This will be the last discussion on this chapter in which we will be talking about its last three subtopics. So just keep on watching and join me as we learn more about logic. Before we proceed to today's discussion, let us first recall the different types of statements that were already introduced in the first part of the discussion for this chapter. And we have this. Note that in each type of statement, they can easily be differentiated since each of them is represented by a unique connective. For instance, the negation statement and its connective not, the conjunction statement and the connective and, the disjunction statement and the connective or, the conditional statement and its connective if-then, and lastly, the biconditional statement and the connective if and only if. In the previous video, we've done discussing about the first three types of statements, the negation, conjunction, and disjunction. And for this moment, we will be discussing these last two types of statements, the biconditional and conditional statements. Moreover, it is also necessary to recall the truth table of the first three types of statements which were presented in the previous video. That is, the truth table for the negation statement given by this, the truth table for conjunction statements, and the truth table for disjunction statements. Let us familiarize ourselves with these tables, for we will possibly be using this as we discuss the last two types of statements. But before we proceed to the discussion on conditional and biconditional statements, let us have first the universal and existential statements. To start with, let us firstly define what are these statements. A universal statement is defined by this. In short, these are statements that state a property that applies to all or that is true to all. For instance, all positive numbers are greater than 0. This is a universal statement since the property that a positive number is greater than 0 applies or is true to all positive numbers. We cannot find a positive number that is not greater than 0 or that is less than 0. Second, for every even integer x, x is divisible by 2. This is again a universal statement, for we all know that all even integer is indeed divisible or can be divided by 2. Third example, ang bawat isa ay may pag-asa. This is also a universal statement because the idea of hope applies to each of us. And lastly, the same thing applies to this last example, ang lahat ng halaman ay nakakain. Kaya this is also a universal statement. Moving on, for the existential statement, it is defined by this. Unlike the universal statement, this statement only requires a property to at least be true to one but not all. In other words, for us to say that a given statement is existential, we must show that the property only applies or is true to some but not all. For instance, there is a prime number that is even. This is an existential statement since we know that the property where a number is prime at the same time even only applies or true when a number is 2. In short, the property applies to some number, in this case the number 2, but not to all numbers. Second, there exists a number which is divisible by any number except itself. This is again an existential statement for the property only applies to 0. 0 is divisible to any number except itself, for when we divide 0 by 0, the result is indeterminate. Next, mayroong isang tao sa mundo na nagmamahal sa iyo. This is an existential statement since in this world, you cannot force or convince everyone to love you. However, we can always find an individual or some individuals who is or are brave enough to love us. Hence, the idea only applies to some but not to all. And lastly, mayroong isang mag-aaral sa MMW na hindi makakapasa. This is also an example of existential statement since this states the existence of at least one student of GEC104 or mathematics in the modern world or MMW who will fail the course. So, for the next topic, let us have the universal and existential quantifiers. Quantifiers are defined as words, expressions, or phrases that indicate the number of elements that a statement pertains to. It has two types, the universal and existential quantifiers. These are quantifiers that are used to indicate whether a statement is a universal or existential statement. For instance, for universal quantifiers, we have this: none, no, all, and every. In other words, when a statement uses any of these quantifiers, that statement is a universal statement. Universal quantifier is represented symbolically by this notation, which can be read as either of the following: for every x, or for all x, or for each x, or for any given x. On the other hand, for existential quantifiers, we have this: some, there exists, and at least one, which is represented by this notation read as for some x, or there exists x, or there are some x. This also means that a statement is existential if it uses any of these existential quantifiers. To understand more about the difference between the universal and existential statements, let us have more illustrations. So for this example, we are to determine the truth value of the following given statements. In doing so, it is advisable to firstly determine what type of statement is presented. The first one is given by this. Note that the statement uses this notation, which we know as we discussed earlier, it is the notation used to represent universal quantifiers. Hence, the given statement is a universal statement. So, since it is a universal statement, for it to be true, we must show that the property applies or is true to all values of x. In the given statement, the values given for x are 1, 2, and 3. Substituting these values to the statement x squared is less than 10, we have this. Note that as seen in the calculation, all the resulting values of x squared are less than 10. Hence, for every value of x, the statement is true. Thus, since the property applies or is true to all values of x, the given universal statement is true. Next example is this. As seen in the statement, it uses this notation denoting existential quantifier, which implies that the given statement is an existential statement. Now, for this statement to be true, we must show that the property is true only for some values of x. So, similarly to what we did in the first example, we will do substitution of the values of x to the given statement. By doing so, we have this. Observe that the statement is true only for values 10 and 20. In other words, the statement applies or is true only for some values of x. Hence, the given statement is true. Now, for the third one, we have this. This is again a universal statement because of the presence of this universal quantifier. This means that for this statement to be true, all values of x and y must satisfy the given statement. But before that, let us first determine the values of x and y. Since the involved variables are x and y, we must obtain all possible ordered pairs using the set of values given for x and y. And to do that, we make use of this mapping to clearly see the possible pairs for these variables. Pairing each value of x to every values of y starting with 1, then 2, and 3, we have come up with these ordered pairs. Now, since we already have ordered pairs consisting of values of x and y, we are now ready to use each pair in substituting to x and y in the given statement. To start with, let us have the first ordered pair, 1, 1. By substituting these values to the statement where x and y are both equal to 1, we have this. Note that with this pair, the statement is true. Now, let us have the second pair, 1, 2. Applying similarly, we have this. For this pair, we have seen that it also makes the statement true. Moving to the third pair, 1, 3, we have this. Observe that the resulting number is 4 and is not prime. Thus, for the pair 1, 3, we can conclude that the statement is false. Since we have shown immediately a pair of values that makes the statement false, we can now stop at this part and directly draw our conclusion since the given statement is universal. Hence, since the ordered pair 1, 3 fails to satisfy the given statement, we can say that we failed to show that all values of x and y satisfy the given statement. Therefore, the statement number 3 is false. Next example is given by this. For this example, we know that this is an existential statement because of this notation. This means that for the given statement to be true, we need to show that the statement is true only for some values of x. Now, like what we did in example 1 and 2, we are going to substitute the given values of x to the statement. And by substituting, we have this. Note that for any values of x, the statement is false. Thus, since we failed to show that there exists a value of x that makes the statement true, the given existential statement is false. For the next topic, we are going to discuss about the negation of the universal and existential statements. To easily construct the negation of these statements, we have this table for guidance which we can directly follow to simply construct the negation. Observe that in the table, it mainly shows that the negation of any universal statement is an existential statement and vice versa. For instance, we have the following illustrations. The first illustration is given by this. Note that this is a universal statement. So looking at the table, we are on the first case. Thus, the negation is given by this formula. This states that to construct the negation, we firstly need to change the universal quantifier to existential quantifier to make an existential statement, and then followed by the negation of the given statement. Applying it to the given statement, we have this negation. It is also correct to have this one instead. Another example, we have this. Note that this is an existential statement. Thus, we are on the second case. The negation is given by this. This time, we will turn the existential statement to a universal statement by changing the existential quantifier to a universal quantifier. Secondly, we will get the negation of the given statement. Hence, by applying, we have this. Now, the third one is this. This is again an existential statement. Just like number 2, we are on the second case, and we will be following the same formula. Hence, we have constructed this negation. For this moment, let us continue discussing more about the negation of the universal and existential statements. However, this time, we will be considering the pattern illustrated by these statements. Presented is the table that will guide us in constructing the negation of every universal and existential statements. In this table, given on the first column are the universal and existential statements, while on the second column are the respective negation. For more understanding, we have the following illustration. The first one is this. Note that the given statement follows the same pattern with this, which means the negation can easily be obtained by following this pattern. Also, note that in this case, our x is the word airports and our y is the word open. Thus, our negation is no airports are open. Secondly, the statement is given by this. Notice that it is of the same pattern with the first statement. Thus, the negation can be formulated by following this. Also, note that in this statement, our x is the word movies while our y is the phrase worth the price of admission. Hence, the negation is given by this. Some movies are not worth the price of admission. Next is this statement. This is of the same pattern with the second statement. Thus, we have this pattern for the negation. So this will be our x and this will be our y. Constructing the negation following the pattern given, we have this. The last one is this, which follows similarly to the third statement. Thus, the negation follows this pattern where our x is represented by this and y is represented by this. By doing so, we have this negation. Now, let us have one last set of examples. In these examples, we are to determine the truth value of the negation of the given universal and existential statements. In other words, we firstly need to determine the negation of the given statement and afterwards, we will determine its truth value. Note that we've done determining the negation of these statements in the previous examples given in this lecture. And to recall, we have these negations. So, what is left with us is determining the truth value of these negations. So again, similarly to what we did earlier in the examples that pertains to determining the truth value of the universal and existential statements, we will be substituting the values of the given variable to the statement, and the conclusion draws based on what type of statement is involved. For instance, in the first example where the negation is an existential statement, we are to substitute the given values of x to this statement. And since the negation is existential, we must show that the statement is true only for some values of x. To start with, let us have the first value when x is 0. By substituting, we have this. Note that 0 is considered to be an even number. Hence, when x is 0, the statement is true. Moving on, when x is 1. By substituting the value, we have this result. We know that 1 is an odd number, hence it is not even. Therefore, the resulting statement is false. Clearly, the statement will not be true for all values of x, since the statement becomes false when x is 1. Thus, we can conclude that the statement is true only for some values of x. Since we have shown a value of x that makes the statement true, it is no longer necessary for us to show whether the values 2 and 3 of x make the statement true or false, since we are dealing with an existential statement. Therefore, the negation is true. For the next one, the negation is a universal statement. Thus, for this negation to be true, we must show that for all values given for x and y, this statement is always true. Just like what we did in the previous example, where the involved variables are x and y, we will also be constructing ordered pairs consisting the values of x and y. Doing similar method, we have this. So now, we are going to test each pair if it satisfies the given statement or not. Note that for the first 3 ordered pairs, that is -1, -1, -1, 0, and -1, 1, we have the following results. This clearly shows that this first set of ordered pairs makes the statement true. There are still lots of ordered pairs left, so we will continue the process. For this time, we will make use of the ordered pair 0, -1. Note that by means of substitution, we have this. Observing the resulting statement, clearly it is a false statement. Thus, since we failed to show that the negation of the given statement is true for every ordered pair, the truth value is false. Similarly, for this example, we need to show that this statement is true for every value of x. So, to start, we will substitute -1 to the variable x in the given statement. So we have this. Clearly, this is a true statement. Next, when x is 0, we have this result. This is obviously a false statement. Thus, since we failed to show that for all values of x, the statement is true, we can directly conclude that the negation is false. Moving on to the next topic, we are now ready to discuss the fourth type of statement, that is, the conditional statements. Conditional statement is a statement that is divided into 2 parts, the antecedent and the consequent. As we introduced earlier, the conditional statements make use of connective if-then. Also, these statements are usually written in these forms, where the antecedent is represented by the P statement and the consequent is represented by the Q statement. Now, For illustration and clearer elaboration, we have this example. For this example, we are to determine the antecedent and consequent of the following given conditional statements. Statement number 1 is given by this. To easily identify the antecedent and consequent of the given statement, let us determine first the structure of the statement. Observe that the given statement is of this form. Hence, since our antecedent is represented by the P statement, we have this. On the other hand, since the Q statement represents the consequent, we have this. Next example is this. Doing the same method, observe that the statement also follows this form. Hence, we have this. The third example is given by this. Again, this is of this form. Thus, we have the following. Moving on for the fourth example, we have this. Note that this statement is of this form. If P, then Q. Thus, we have this. And lastly, we have this. This is again of this form. Thus, we have this. For this part, we will be introducing more equivalent forms of a conditional statement aside from the two forms that were introduced earlier. So now, these are the other forms representing conditional statements. To familiarize ourselves with these forms, we have the following illustrations. In this example, the given conditional statements is written in the forms other than its usual form, the if-then form. So for this, we are asked to rewrite the statement in that form. For number 1, we have this conditional statement. Note that the statement is of this form. So following the pattern given, we have identified the P and Q statement. Hence, the statement is written equivalently as this. Moreover, since the pronoun refers to the word number, we can also have this answer. Next, we have this. For this statement, it follows this form. Thus, we have this P and Q statement. Therefore, we can rewrite the given statement as this one. Next example is given by this. Note that the statement is of this form. Thus, we have the following. Observe that what we obtained are the statement Q and the negation of the statement P. So we need to construct the statement P using the negation of that statement for us to finally write the given conditional statement in if-then form. To construct, we will just negate the not P statement, which results to this. Hence, we can now rewrite the given conditional statement in this form. And lastly, we have this. The given conditional statement follows this form. Therefore, we have this. Observe that the thought of the statement fails to hold if we directly construct the conditional statement using the obtained P and Q statements. Thus, to be understood clearly, it requires proper sentence construction. Hence, we have this. Or, we can also have this. Moving on to the next part, like the other type of statements, we also have the truth table for conditional statement and is given by this. This table presents the truth value of the P and Q statements together with the truth value of the conditional statement. This table also shows that the conditional statement is false only if P is true and Q is false. On the other hand, it is true in all other cases. But before we proceed to the next one, let us keep this first in mind. This states that a conditional statement where the involved P and Q statements are open sentences is true if and only if the truth set of the open sentence P is a subset of the truth set of the open sentence Q. Moreover, the negation of any conditional statement is symbolically represented by this. It can easily be constructed by forming the statement given in the table. For instance, in this example, we are asked to determine the truth value of the following given conditional statements. The first one is given by this, where the P statement represents this, while the Q represents this. Now, to determine the truth value of this conditional statement, we firstly need to determine the truth value of the P and Q statement. The P statement states that 2 is an integer. Recalling your previous topics in your mathematics subjects, particularly on real number system, we've learned that 2 is a natural or counting number. And this set of numbers is a subset of a whole number, which is also a subset of integers. Hence, we can also say that 2 is an integer. Thus, our P statement is true. Now, we've also learned that the set of integers is a subset of rational numbers. Therefore, since 2 is an integer, 2 is also a rational number. Hence, the Q statement is also true. For this moment, we can now determine the truth value of the given conditional statement. Recalling the truth table given earlier, we can see that since both our P and Q statements are true, we are on the first case. Therefore, the given conditional statement is true. Next, we have this. Similarly to what we did in the first example, we will determine first the P and the Q statement. And these statements are represented by this. Next, we will determine their corresponding truth value. Obviously, both P and Q statements are false. Hence, by referring to the truth table, we are on the fourth case. Therefore, the given conditional statement is true. Now, for the third example, we have this. In this conditional statement, the P and Q statements are given by this. Note that the P statement is true while the Q statement is false. Looking at the table, we are on the second case. Hence, this conditional statement is false. Next, we have this. Note that in this conditional statement, this is our P while this is our Q. Now, let's determine the corresponding truth value. Note that the P statement can be written equivalently as this one. And we learned in the previous video on chapter 3 that this is a disjunction statement. So, for us to determine the truth value of the P statement, we need to determine first the truth value of this disjunction statement. Observe that we have these following truth values for this statement. Recalling the truth table for disjunction statements, we can see that we are on the second case. Thus, our P statement, which is the disjunction statement, is true. Now, for the Q statement, this is clearly a false statement. So, recalling the truth table for the conditional statement, we can see that with the truth values obtained for P and Q statements, we are on the second case. Therefore, this makes our conditional statement false. And for the last example, we have this. So this is our P statement and this is our Q statement. Observe that both the P and the Q statement are true. Therefore, referring to the truth table, we are on the first case. Hence, the given conditional statement is true. Moving on, we have another set of examples. In this, we are going to provide the negation of the given conditional statements. Firstly, we have this. Note that this conditional statement is of this form. So with this, we can easily determine the P and the Q statement. In fact, we have the following. So recalling the symbolic representation of the negation of a conditional statement, we have this negation. Alternatively, we can also have the negation like this. The second statement is given by this, which is of this form. Hence, the P and the Q statement are represented by this. Recalling again the symbolic form of the negation of any conditional statement, we have obtained our answer. The next example is given by this. This statement follows this form. Thus, we have the following. Recalling the negation of a conditional statement, we have constructed the negation for the third conditional statement. Moreover, it is also correct to have this negation. And lastly, we have this conditional statement. This also follows this form. Hence, we have the following P and Q statements. Observe that the Q statement can also be written as this, which is obviously a disjunction statement. In our previous discussion, we've learned that the negation of a disjunction statement is formed by this. Hence, the negation of our Q statement is given by this. And now, with the help of this table, the negation of the given conditional statement is this, which can also be written as this one. Now, for the next topic, we are going to discuss the derived conditional statements. That is, the converse, inverse, and contrapositive. The converse is denoted by this, which is formed by interchanging the antecedent and the consequent of the P and the Q statement. For the inverse, it is denoted by this, which is formed by just negating both the antecedent and the consequent, or the P and the Q statement. And lastly, the contrapositive. This derived statement is denoted by this, which can be constructed by getting the converse of the inverse of any conditional statement. For this example, we are asked to give the converse, inverse, and contrapositive of the following conditional statements. Now, for the first conditional statement, we have this. So, this is our P and this is our Q. For the converse, again, we are going to interchange the P or the antecedent and Q or the consequent. Thus, by doing so, we have this. Next, for the inverse, we are going to negate the P and the Q statement. Note that the negation of the P statement is given by this, while for Q, it is given by this. Hence, we have constructed the inverse of the conditional statement. And lastly, the contrapositive. This is formed by getting the converse of the inverse of a conditional statement. Thus, by using the inverse obtained earlier, we have this statement. Next example is this. This is our P and the Q statement. For the converse, we are just going to repeat the same method we've done earlier. Thus, we have this. For the inverse, we firstly need to obtain the negation of the P and the Q statement. Hence, we have the following negation for P and Q statement respectively. Moreover, we have this inverse. And lastly, for the contrapositive, just get the converse of the obtained inverse. Hence, we have this. The second given conditional statement may also have the following converse, inverse, and contrapositive respectively. For the third conditional statement, we have this. In this statement, this is the P and the Q statement. Now, for the converse, it is given by this. On the other hand, the inverse of the given conditional statement, where the negation of P and the Q statements are this, is written as this one. And for the contrapositive, it is given by this. Moreover, the derived conditionals for this conditional statement can also be written as this one. And lastly, we have this. Observing the structure of the given conditional statements, we have located the P and the Q statement. Similarly to what we did in the previous examples, the converse is written as this. For the inverse, where the negation of the P and the Q statements are given by this, it can be written as this one. And using the obtained inverse, the contrapositive is written as this. Now, for the next discussion, we are going to present here the truth table for the derived conditional statements. Observe that in the truth table, the conditional and contrapositive of a conditional statement have the same truth values. Furthermore, we also observe that the converse and the inverse of a conditional statement also have the same truth values. In other words, we simply conclude that the conditional statement is equivalent to a contrapositive of that conditional statement, and the converse and the inverse of a conditional statement are also equivalent. To understand more about the derived conditionals, we have these examples. In this example, we are to determine the truth value of the converse, inverse, and contrapositive of the given conditional statements. For the first example, we have this. To make it easier for us to determine the truth value of these derived conditional statements, let us first determine the truth value of the P and the Q statements separately. Observe that the P statement is indeed true, since the month of January really consists of 31 days. However, the Q statement is false, since the month of June consists only of 30 days. Now, recalling the truth table presented earlier, we have seen that we are on the second case, which implies that we are expecting to have these following truth values. Hence, the converse is true as well as the inverse, while the contrapositive is false. Next example is given by this. Applying same process we've done in the first example, we have the following truth values for the P and the Q statement. Now recalling once again the truth table for the derived conditional statements, we've seen that we are on the third case. Thus, based on the truth table, we can conclude that both the converse and inverse are false, and the contrapositive is true. Moving on to this third example, we can say that the P statement is true, for indeed President Rodrigo Roa Duterte is the current president of the Philippines. And it is also true that former DILG Secretary Mar Rojas lost the 2016 presidential election. Hence, our Q statement is also true. Now, looking at this truth table, we are on the first case, which means that we have these truth values for the derived conditionals. Thus, the converse, inverse, and contrapositive of the given conditional statement are true. For this last example, the given conditional statements consists of open sentences, so we will be solving it quite different to what we did in the previous examples presented. So for this, we need to obtain first the truth set of the P and the Q statements. Now, looking at the P statement, we know that the truth set is given by this. On the other hand, for the Q statement, the truth set is just this set. Recalling our discussion on the truth table of a conditional statement, we've noted that the conditional statement is true if the truth set of the P statement is a subset of the truth set of the Q statement. Thus, observing the obtained truth sets, we can see that the set P or the truth set of the statement P is not a subset of the set Q or the truth set of the statement Q. Hence, the conditional statement is false. Since the conditional statement is equivalent to its contrapositive, the truth value of the contrapositive is also false. On the other hand, we can see that the set Q is a subset of the set P, which implies that the converse Q implies P is true. And since the converse and inverse are equivalent, the inverse of this conditional statement is also true. Now, for the last topic on this chapter, we have biconditional statements. A biconditional statement is defined by this and is denoted by this symbol. This can equivalently be written as the conjunction of the conditional statement and its converse. Just like the other types of statements, we also have specific truth table for the biconditional statement and is given by this. So note that the table clearly shows that the biconditional statement is true if and only if both the P and the Q statement have the same truth value. For illustration, we have this example. In this, we will be determining the truth value of the following given biconditional statements. So for the first one, we have this. Note that both equations are true when x is equal to 3, as shown in the illustration, and both are false when x is not equal to 3. Since the equations have the same truth value for any value of x, we can say that based on this truth table, we can see that we are either on the first or last case. Both cases results to a true biconditional statement. Hence, the given biconditional statement is true. Next example is given by this. Observe that both equations are true for x is equal to 6, as reflected on the solutions provided. However, when x is equal to -6, we can see that the first equation is true, but the second equation is false. Now, this implies that P and Q statements have different truth value, and referring to the truth table in particular, we are on the second case. Therefore, the biconditional is a false statement. For the third example, we have this. Obviously, both inequalities are true for any values of x greater than 7. Likewise, they are both false for any values less than 7. However, when x is 7, we have this. This shows that the first given inequality becomes false while the second is true. Now, referring to the truth table, this lies to the third case. Hence, the biconditional statement is false. And lastly, we have this. Observing the involved inequalities, we can see that both the inequalities are true when x is greater than 2, as shown in the solution provided. Moreover, when x is less than or equal to 2, they also have the same truth value, but this time it is false. Thus, referring to the truth table, we can say that this lies either on the first and last case. Hence, the given biconditional statement is true.